Thank you. Hello, everyone. Thank you for joining us from different time zones. Today, we are joining here for the session Education Class 1, which is titled A Hitchhiker's Guide to System Security, the Art and Science of Building and Breaking Secure Computing Systems. The session will be handled by Professor Ahmad-Reza Sadeghi, who is a full professor of computer science at the Technical University of Darmstadt in Germany, where he heads the System Security Lab. Since 2012, Professor Sadeghi established a long-term cooperation with Intel. Moreover, he also established the Open Lab for Sustainable Security and Safety, Open S3 Lab, which is called in short, with Huawei in 2019. He has been leading and involved in many national and international research and development projects in the area of design and implementation of trustworthy computing platforms, hardware-assisted security, IoT security and privacy, applied cryptography, and trustworthy AI. Professor Sadeghi has been serving as General Chair, Program Chair, as well as Program Committee member for major venues such as ACM, CCS, IEEE Security and Privacy, NDSS, Usenix Security, DAC, DATE, ICCAT, just to name a few. He is also co-initiator and co-organizer of the world's largest hardware security computation hack event that is taking place since 2018 in these top-tier venues. In 2008, Professor Sadeghi has been awarded with the renowned German prize Karl-Heinz Becker's for his research on trusted and trustworthy computing technology and its transfer to industry practice. In 2018, he received the ACM SAC Outstanding Contribution Awards for dedicated research, education, and management leadership in the security community and pioneering contributions in content protection, mobile security, and hardware-assisted security. We, the ESWeek 2022 team, are very grateful to Professor Sadeghi for being with us today. All of us here are eagerly waiting to hear his take on system security. So over to you now, Professor Sadeghi. Thank you so much for joining us.
Okay, thanks a lot for a very, very nice introduction. You didn't need it actually to do that. And thanks a lot for the invitation. So I'm happy that I got the time right, because when you give a talk virtually and there are so many different time zones, and thanks to the organizers, I've heard that it is not really easy task to organize such a lectures, and people who are benefiting from these lectures, at least I hope that they benefit from these lectures, must hopefully know the value of it, value of the effort that organizers put in it. I organize myself a number of workshops and conferences or co-organize them. And I'm myself very involved in that, and I know how hard it is to do that. Okay, so the title was actually the title that I gave to the organizer was too long for this first slide, so I made it a bit shorter, and I decided to do it yesterday because I used this title also in other contexts. But the Hitchhiker guide is indeed about the lessons that I myself learned in the, let's say, in a long time with a number of PhD students, postdocs, and assistant professors. This talk is a more about what were some achievements of security community in general, both in software and regarding software and hardware security. It is not a talk where we are talking about a specific paper of my group or any other group. It is about what is my own experience, because I have been in industry for many years before I joined academia. Actually, before I did my PhD, I was working for big telecommunication companies, and security was not my focus. But Then when you change to academia, you have a completely different world, a different universe. And in that universe, you go back and work with other, so to say, companies, some those companies that you have been working for, or those companies that are just coming to you because you are doing some interesting research for them. And in that context, I had the opportunity to work with a number of large enterprises all over Europe and the US, but also in Asia. Certainly my experience in the past by being in different industrial sectors helped me a lot to understand, because you need to understand the language of industry. And then I decided at some time, and I will explain that to those who are participating at least, to understand what is actually the problems that usually you don't get disclosure of the problems that certain companies have. And then these problems can be very non-trivial. So it is indeed, they are not always development problems that specifically bigger companies have. There are some very interesting problems to solve that have lots of scientific value, and by solving them, or at least by attempt to solving them, you will gain a lot of insight. And I hope that during these 2 hours, because we started a bit a bit later, so I timed this talk for 2 hours, and I hope I can give you some insight about what was my experience. So let me start with something that is following me since I am, I don't know, 16 years old or 17 years old. And this is a quote from Nelson Mandela, and I hope most of you know who Nelson Mandela is. It is about, of course, this statement, "It always seems impossible until it is done," is valid for everything in life, but also for scientific achievements. But if you look into the security in general, so cybersecurity, whatever relates to security of systems that we are working in, and we all know here we are using a digital session. And since I now understood that everything is organized in China, and we had a pandemic, and in this pandemic time, we learned that many people need to use digital technology in different ways. And this is why the number of cyber attacks increased a lot. The number of, at least in Europe and in Germany, the number of physical robberies went immense down. The number of but the number of cyber attacks increased very rapidly, because we still, the whole humanity does not have the right, so to say, security for all these complex systems that we are generating more data, we are generating more software, and the hardware which is underneath it is not, the security of these systems is not clear, both in hardware and software. So, and in my career, everything that I have done is indeed based on this quote. Somebody said, this is not possible in cybersecurity, the system cannot be attacked. And we found a hole in it with, of course, very smart PhD students. For that, you need, of course, good resources. But this is something that in cybersecurity is really everyday's business. So let me give you a kind of overview of the content of this talk, and that this is about not only my own journey, but the journey of many, many other colleagues. And you should know that it is not a comprehensive talk, because I cannot cover 20 years of research in 2 hours. But I just picked those aspects that I thought it's very important to see how a trend comes up and how this trend goes down in a research community, and also having a critical view towards what we are doing in research in the security community. Okay, so the motivation of many researchers, specifically in security, at least my motivation was secure distributed computing. So this is the holy grail problem to solve. What does it mean? You have a distributed system and they are communicating, they are connected with each other. And it doesn't matter what kind of devices you are concerned with. It could be a mobile phone, it could be a sensor, but in general, any device. And when they are communicating with each other because they are together providing, so to say, the foundation of certain computation, then you would like that to happen securely. What in general, it means that if a part of system is attacked, the main functionality of the system should still be alive. So this is the ultimate goal. And you can see that most countries today, even in the most advanced technologies, their critical infrastructure, which is one part of the distributed computing, is in general not secure, specifically when they want to connect to the general internet. So, and this is why some really go towards private networks, which are also attackable, but it is more, you need more effort. So, but we are talking here more about the technology, but not about social networks. This is another problem for itself, but secure distributed computing is the general motivation, at least for me. Now, starting with that, if you are familiar a bit with cryptography, this is where I did my personally my PhD in a really hardcore cryptography. Distributed computing is or secure distributed computing could be kind of reflected in the general concept of secure multi-party computation. You have a number of parties, they compute something, they don't want to reveal their inputs, so the inputs are private, and then they want to compute something in a secure way so that nobody can cheat. And at the end, they get the outcome. The outcome can be known to everyone or to some of them, like for example, voting system. The outcome is only known to you. You know that you have voted, but not to others. Others should not know what you voted. So this is a general concept of secure multi-party computation. However, when you want to do it in cryptography, you try not to trust any software or any hardware, any other entity. But in reality, our systems are made of software and hardware. So the episode 1 of this talk will be about runtime attacks and defenses. So how people try to, so runtime attacks means that during the runtime of the program, the adversary compromises the program. And runtime attacks and defenses really dominated the security community. And when I take security communities, really all the top conferences for a long time. Okay, this is of course for me it was first frustrating because cryptography was not the answer. Cryptography is only a tool. It has some mathematics, which is nice, but in general, cryptography is the least problem, I would say, that we are concerned with. We are concerned with really big, huge chunk of code that is written because of legacy systems, and it is still has a lot of vulnerabilities. This was why you see this small guy here that is a bit of frustration. So I started with runtime attacks and defenses. I will come to that. And then the next problem was that you will see when you get into the runtime attacks and defenses and try to find solutions, as we will see in short, you will soon recognize after some years that you need to make certain assumptions. So many research papers at the beginning, they assume that, for example, operating system, which is a huge amount of code in general, and specifically commodity operating system, we know that they are not secure because they were not made with security in mind. And that's the problem. And then so you ask yourself, okay, if I don't want to trust this huge chunk of code, and I cannot prevent all the attacks that can happen, so what about getting support of hardware? So in 90s, thousands of papers and also standardizations activities started in the context of the so-called trusted computing. And the idea of trusted computing is very simple. It said, we have our commodity systems. We cannot replace them with secure systems because it is expensive. It needs a redesign of everything. This is really impossible, a very big task. In a so to say very limited area, yes, scientists do that, engineers do that, but in general, how about adding or integrating certain small components in an existing system? These small components, they have certain features that are verified, but they are small components. Small means they have a small set of features that are security critical. These features help us to fulfill much more complex security requirements. So you have a small set of features. For example, in cryptography, you can do encryption and hashing, cryptographic hashing. And then you say, but with these two functions, I can build a system that fulfills more complex requirements. That is the abstraction of the whole idea. So, and then it throughout since 90s to now, we have something that I call enclave computing, and I will come to that. That means running your software in a secure environment, that you have those features, you trust those features, that they are not, they don't fail. And then you run your software, and then you can assume that you do not trust your operating system, for example. So you get rid of a big chunk of code. You don't need to do any assumptions. You don't need to do anything. So that's actually a cool idea if you can realize it in practice. Now, after doing this, you will also recognize that there are a number of problems, and we know this in the last 10 years, that enclave computing needs hardware. So, and those functionalities I was talking about, some people talk about trust anchor, some people talk about secure functionality, but in general, or trusted computing base, this is the general term for it. If you, in reality, in practice, you need these features to be also in hardware, and hardware gives you specific support. Now, we know in the last 10 years that hardware is under attack, and the number of hardware vulnerabilities that are security critical, they are increasing. And the reason is that people are reverse engineering the existing processors, the existing hardware. And I'm not talking about here about hardware attacks. That means you have access to hardware, and you do, for example, the traditional side channel attacks by really touching the hardware, by trying, for example, to peel your chip with acid, trying to put digital analyzer on it. Even if you touch a bus on your system, this is considered as hardware attack. I'm talking about something that I personally find it much more interesting, is that an attacker is sitting at home and is attacking your system, but by knowing hardware vulnerabilities in your processor. This is has much more, so to say, much more scalable than just accessing the hardware and putting it in a lab with lots of other devices connected to it to find something in there that is like, for example, a cryptographic key. That is a typical example that you can see. So hardware security became itself. So we came from distributed system, very high level security, to individual components. And then we go to hardware security, where now, if you see that because of geopolitical problems, hardware security becomes very important. All big, so to say, all countries who have the technology, they are trying to provide, or technologies provide means, financial means, for producing their own chips. And this is coming back because of wars and because of concern and because of politics. Hardware security will become much more important than any other research in security, because if this goes like this, that billions of dollars are invested in making hardware at home in own country, but then if it's not secure, what do you do? Or if I don't trust the hardware coming from another country. Okay, so hardware security is something that we have to look into it, because hardware is at the heart of any critical system, any computing system. Once I know a vulnerability in hardware, then I can break any system if I want, as it has been shown many, many times in the last 10 years. Okay, so on the last part of the talk, this lecture will concern on something that I call, this is pure research, something that I call adaptive security for hardware, which is also not trivial. Why adaptive security? Because the problem with hardware is it's not like software. You cannot patch it immediately, not always. There are things that you can use changing microcode. There are configurability aspects in some systems that there is one component that you may be able to configure, but it's not always concerning security. And this patching and really filling the holes in a system does not really help us in the long run, because once an attack is out, you fix it, but there's another attack coming. Yeah. And because of complexity of processors of today's processors, we can't really say, even if you have fixed something in the microcode, then somewhere else you don't have a problem, because they are connected. There are lots of hardware IP blocks are connected to each other, and we need a radically different approach to that. And this is something that I may be able to talk about depending on the time. So I took time here to explain to you that this is a kind of historical view of many areas that I worked in it, because I didn't want to focus on only one thing. Some researchers focus on one thing, and maybe one day they solve a big problem, and maybe they never solve the real big problem. They solve small problems. My history is different. They are somehow connected to each other, but it was always really according to these pictures. There was frustration in one area, saying this is not enough, go to look into another challenge, and then you see, oh, this challenge cannot be solved simply, go to another challenge. And of course, it has also to do with trends and what is possible to do in research. It's always not, it's also funding and all these kind of things that is not of interest in this talk. But anyway, so this is the whole story, and let us start with the episode 1, which is the runtime attacks and defenses. So runtime attacks and defenses are a never-ending story. It's really an arms race that has been there for more than 3 decades. And why? Because most of the vulnerabilities that we know in our systems, I'm talking now about software systems, is on memory safety. So this is a major cause of vulnerabilities. Almost 70% of vulnerabilities in software are related to some memory corruption, like because we are still in many commodity systems, also operating systems. We are using languages like C and C++ because of efficiency, and still people are programming in these languages for when you want to get something fast done. We have assembler. They all have their own security problems, and you cannot, at least currently, we cannot program everything in secure languages. And I will come to that a bit later when we talk about secure languages. So, but just mentioning that it's a pity that we don't have, at least in our security community, we don't have much, or let's say not a significant, or at least it is insignificant number of papers on this topic. And the language community is a completely different community. So knowing that, and as I said, 3 decades, so the very old attacks were based on code injection, or at that time it was less code injection, it was like a computer worm, but there you also need to trigger some aspect of system, and code injection was one of the most known attacks. However, as the time passed and more researchers got into the security, and security as a science that you can really, on cryptography belonged to industry and intelligence services for many years. And then in 70s and 80s, the first publications came out in the area of cryptography, I mean, more academic aspects of it. And since it was always secretive, so many things were actually also not secure, but they used it. And later on, other researchers as cryptography and information security became a real discipline within electrical engineering or computer science or mathematics department, and then it became itself a discipline. We had more insight. So one of the insights at the beginning was, oh, we can inject codes, for example, through a buffer overflow. You may have heard about buffer overflow, but it's not important here. In buffer overflow, many students have it now in their classes. Like a simple one is you write a program and you don't do bound checks. So if your array can be written in an arbitrary length of input, then people came to the idea, oh, I can do that by putting an executable file into this array, and at some place the system automatically executes this. I just need to tell to the system, go to that code. Yeah, so that was a very at those times, that was a big thing, a big achievement, because all computer systems were most of them were not really made for security, with security in mind. But later on, after code injection, as you can see here, for example, in this slide, I wrote there, memory corruption attacks, code reuse. And this is what is more or less state of the art. Code reuse is much more complex and also much more sophisticated. It can also include code injection, but it doesn't need to. It can it can create the environment for code injection. And you see here a control flow graph of a program. And these nodes are basic block. They are called basic blocks. They have a single point of entry and exit. They contain assembly instructions. So, and then they have branching in your any program has some kind of branching typically, and this branch can be direct. So target address is encoded into the instruction, and it can also be indirect. Yeah, so target address is saved in memory. Yeah, it's a writable memory. Now, code reuse attacks, they do not inject code. They just use the code that is already residing in the application memory. And one class, an important class of these attacks that has been the focus of research for many years, starting from, let's say, officially maybe from 2006, many groups in this world try to solve the problem at least first do the attacks and also defenses. It's control flow attacks. So you overwrite code pointer, you change the control flow of the program. As you can see, the red ones are that's changing the control flow. It is not what is meant by the programmer. Now, if the adversary can do that, then it can chain the existing code together and then run. It has been shown that the adversary can run arbitrary code execution. That means something that it is known as Turing completeness. So it means that in these basic blocks, there are assembler instructions, and then you find in beforehand the adversary knows which assembler instructions provide the so-called gadgets, and these gadgets perform particular tasks like load, store, XOR, or branching, or whatever the adversary is aiming at. So the adversary can redirect or misdirect the flow from B, for example, to F, because here there is a chunk of code that the adversary needs to run the attack at runtime. Sounds a bit like magic, at least the first time I've heard about it, like, wow, this is a wow effect. And the reason was that code injection became, so let's say buffer overflow became more difficult. The industry and researchers, they understood the problem of code injection and tried to prevent it by some memory safety actions in the hardware. Microsoft put measures in their system. So code injection directly, so misusing buffer overflow, became more difficult. Okay, so there are a number of ways to fight code reuse attacks. First of all is training developers. When the software is developed, you have to check that you don't provide any way, so to say, any means to launch a code reuse attack. Usually, code reuse attack, certainly the starting point of a code reuse attack could be a buffer overflow. But then, because of the new defenses, defenses that are known for 20 years, you cannot execute code. You can just put information into the buffer, but you cannot execute code. So this information is exactly the starting point of code reuse attacks. These are pointers. So the adversary puts pointers and return addresses in this buffer, but the starting point of any code reuse attack is a memory safety problem. And buffer overflow is one of them. There are also many others, stack overflow, this overflow, that overflow, yeah. So training developers is only partially effective. Developers cannot get a super education in security of how to securely write code and be efficient. So, and on the other hand, just think about it, if developers are all security experts, then there will be no security disciplines, because developers, I mean, they will know nothing to do with research, just think about it. So developers should develop, yeah, and we cannot really educate them because then they may think, oh, developing is boring, because they see, oh, there are very nice research problems. Let's become a researcher, yeah. And then how can Google hire so many people with PhD and let them program stuff and call it research? Yeah. Okay. So then the other aspect is having new languages. Yeah. So this is a very important thing. New languages for systems that I come. There are lots of attempts to or people build secure languages. For example, yeah. If you think about so-called type-safe languages like Java, but you can't write an operating, at least currently, nobody writes an operating system in Java because it would be a problem with efficiency maybe. And there are lots of legacy code there that you don't want to replace. Nobody has the financial and resources for it. And so it is very important, however, I think, to have secure languages. And there is a community, language community is doing research in this area for years. And the pity here is, unfortunately, security community and language community, they do not always talk to each other. And I think this is an effort that security community should do, so that we have also accept more papers at security conferences on secure languages. Another aspect is finding bugs. Those of you who have heard of, let's say, formal methods and formal verification, which was used originally for finding functionality bugs. Formal method community started to also look into the security aspects, and formal method is, the good thing is formal method is that it gives you some, so to say, you can reason about having a assertion in your system, reason about a property in your system. So formal method is important specifically from scientific point of view. However, formal methods and many tools, many tools have been developed. Millions of, maybe even billions of dollars have been put into that, because many companies need to verify their system, at least for functionality, and in the recent years also more and more for security, in an automatic way, but also in a way that they are assured it is reasonable. Reasonable, that means it is, you can reason about it mathematically, for example. However, the more complex the system becomes. Any question? So I hear someone, otherwise please mute. So and finding bugs, formal method has its limitations. For example, state explosion is a very known problem. When the system is too complex, you cannot cover all the possible states in a system. And of course, in some cases, you need manual effort to formalize or to define security properties. And this is very, very tough in complex systems where you have interaction between a lot of modules and so on. So, but these are important tools. The last thing that you can do is, of course, preventing the attacks. Preventing the attacks. And this is what we are going to a bit, so to say, concentrate on. So, what is then preventing attacks? I'm now going to accelerate a bit. Preventing attack is trying to not let the adversary run these control flow attacks. And I'm talking only about control flow. I'm not talking about even the data oriented attacks, which is a really sub-discipline for itself. I'm talking about the most publications that are control flow attacks. So here we know that if the adversary can launch such an attack, where when the adversary has knowledge about the memory address space. So the adversary knows, for example, where are the addresses in basic block F. If the adversary wants to, for example, jump at the beginning of this basic block, which was not meant in the original program, as you can see in the control flow graph. So the adversary requires exact knowledge of the memory layout, and one very simple method against it is just use randomization. You randomize in a different way with different granularity from randomizing an offset. Most of you have heard of ASLR, which is done in every operating system, in commodity operating system, in every system is using that. So randomization-based defenses are low performance overhead. They have low performance overhead. They can have different granularities. For example, you can go up to the scale of instruction, and they scale to very complex software like your browser. However, they have also a downside, which is the entropy. In many systems, you don't have enough entropy for randomization, and they are vulnerable to memory disclosure attacks, as I'll come to it in some minutes. Another way of, so to say, protecting systems or preventing control flow attacks is add instrumentation. So you instrument your code. Check if the next basic block is either C or D in this picture. If not, raise exceptions. This defense is called control flow integrity, which was known for some years. And the community started to integrate this idea into the code, instrument the code. And the positive side is that it gives you some formal security guarantees. And when I say formal security guarantee, it means that if you take care that B always goes to D as the programmer meant, yeah, and not be redirected to F, that means you always label B, and here you do a check, does B go to D? And if not, exception. If yes, continue. You can prove that your program does what you want. So the execution path is as you want. However, the problem is the trade-off between security and performance, as we will come to it, and it often requires adjustment to the protected application because you need to instrument your application, and sometimes you only have binary. And if you want to instrument your binary, you may not have all the information that you want to protect your code. Now, for the first part, which is randomization, so randomization, maybe we'll go back. Randomization methods are used in the bigger context, which is called software diversity. Yeah, so you know the same software should not, when it is downloaded to the client devices, they do not look alike because they are randomized. Yeah, they do the same functionality, but the address space is randomized, or the instruction is randomized. Yeah, the addresses. So now the question is, if we have very fine-grained randomization, so we go up to instruction randomization. Yeah, usually people go up to function, so the addresses of functions are randomized. How good, how secure? What are the security requirements in our system, and whether or not fine-grained randomization can protect against them? This was the question that my group, but also with several colleagues in US, we were discussing this. And certainly, we wanted to know how good randomization can be. So we started to look into the randomization and build a defense and say which system should have which granularity of randomization. Unfortunately, this project led to a very negative result. And what was this result? It came to a paper, which at that time we called it just-in-time return-oriented programming. Return-oriented programming is a method of cause reuse attack. That means you misuse, the adversary misuses return addresses by putting himself return addresses where the program execution follows these return addresses, and then it executes codes where these return addresses are. So return addresses are very important to be protected. Now, this project, we put in a number of students, I think there were 6, 7, or 8 students together with us. We met every week. We were 3 weeks together, and we started to look into all randomization and see if we can build a very nice system with that. And at the end, we found out that one group of students broke everything that the other group designed. And here you see, assume that you have an application, and these are here's how the attack works. These are the basic blocks. And assume that in one of these basic blocks, and maybe I just tell you what the adversary can. So we have these basic blocks, and here this one is not randomized. Everything else is randomized. Yeah? The adversary doesn't know where the addresses are. So we just keep this one first free. At least I will tell you what is not randomized there. So what are the adversary's capability in the adversary model in code reuse attacks is the adversary can read memory, can write to the memory, and the adversary may have access to a scripting engine, for example, a browser. That doesn't mean that the adversary is controlling the browser. It means that when the browser runs and you, for example, look at the PDF, the browser engine, the scripting engine is working automatically. So you don't need to control it. You just need to say, open this PDF file that users does, because user clicks on a PDF link. Yeah. So now, in this basic block, we give to the adversary an auxiliary information. That is one address to one code pointer. Yeah. So that is the address where I know this is the real address of in the code. Yeah. So it is not randomized. We just get one, okay, one code point. Now, the adversary tries to read from the memory, from this basic block, and it gets a memory page. And in, for example, many computers, computer architectures, we know how the memory layout is built in. That means the boundaries of a memory page. For example, in Intel, it is 4 kilobytes. Yeah, so a memory page. But actually, the adversary sees only numbers, nothing else. Yeah, that doesn't help the adversary. Now the scripting engine, like the browser that for example, your PDF is now running in it. The adversary is using this scripting engine or misusing it. As I said, it is running itself to disassemble, but the adversary has already prepared everything that this part, because the adversary knows this address, is disassembled. Now the adversary sees all the code here, and it knows this code pointer. So assume that this code pointer is somewhere here, and for example, it is at, I don't know, call B. Yeah. So if the adversary knows the code pointer and knows the boundaries of the memory page, after the disassembly, the adversary sees this part of code. And now this code has a, for example, something like call B in it, and this is an address here. So the same procedure is followed, and then you get the code on this memory page and so on. So this goes further, because the user is browsing a PDF, and this code payload is in that PDF. Yeah. But note that everything starts with the vulnerabilities. The adversary knows a vulnerability somewhere in the code, and then the user clicks on the PDF. The PDF is running in the browser, and the browser automatically does what the adversary wants. Now, the adversary has access to a lot of code now, and the adversary also at runtime knows what it needs to put together those gadgets to run the attack. For example, opens, this is a typical thing that people do, opens a window where you can give commands in it, yeah. So, or adversary can give remote commands. So this attack has shown that it breaks every randomization scheme. And that was, for me personally, a kind of, so to say, turning point, that all these randomization schemes are interesting. They help to some extent, but they are not what you're looking for. So randomization schemes are vulnerable to information leakage. So one code pointer, and then you are done. You don't even need a code page. Now, later on, some colleagues who were in diversity community talked to me and said, hey, and that's a very interesting story. I don't want to tell you the story now, it's long, but short. They said, hey, when we send a paper to a conference, then they, because I use software diversity, they say, hey, are you secure against JITRO? And they reject our paper. So, and I said, okay, let's look together instead of fighting. Let's look together if we can find a way around it, yeah. And then we started to work on something which we call Redactor in publishing SMP 15 towards resilience to memory disclosure. That is, we wanted to prevent this, and that means that you don't give the part where the code is executed. It is executed only. You cannot read anything. And we applied it to Chrome. It was a long project because we wanted to have a complex software like Chrome, and it should run this randomization. And we also tried to implement it for mobile systems. However, note that there is still a window of attack here. For example, in a system where you have just-in-time code, when the code is created at runtime, because there are some fancy functionality of a browser, then there is a window where the system can write and read and as well execute. And in that window, you still, if you find that window, you can make it very small, but still when you find it, then you can attack the system. So these are, from academic point of view, are not really the perfect system that we want, but from a practical point of view, you can say that we put effort to at least going towards resilience to memory disclosure, because memory disclosure is kind of like a side channel, and it's very, very difficult to prevent in a complex system. But what was interesting about this project was that part of this project, a module for randomization, was used in Tor browser, because there was an attack on Tor browser. I hope that everybody knows Tor. Tor is a, so to say, anonymization network used to hide your identity, in this case, for example, IP address. And then there was an attack on the Tor browser, because browser is used to make it easy for users to use the Tor system, and that was very interesting to work with Tor project, because I know them, I know most of them, and it was very fun, at least for students, back and forth with them to get the randomization parts that we made into the Tor browser. I'm not sure that they are still using it, but at that time it was a hot topic. So now that was randomization, and let's come to the next part, which is on control flow integrity, and we are still in kind of in software. We're not going to hardware now. That comes. So now, CFI in practice, the general idea you already saw, but in practice, you need to label every node here. Yeah. So as you can see, there are many labels, and in a very complex system, you have thousands of or millions of labels. So now checking all of them takes a lot of time, and nobody wants to wait for a Chrome browser when you scroll it and the CFI is running, which is because the code is instrumented, and you need 1 minute or 2 minutes to scroll one page, you will get nuts. Yeah, so you don't do that. Now, people started to reduce the number of labels, and one idea was to reuse them. However, when you reuse them, you also increase the attack surface, because then there are illegal or illegitimate ways that the adversary can find between the nodes. Okay, so this was a problem, and a number, actually hundreds and hundreds of papers were written on how you can make this more efficient, but also try to fulfill some security requirements. And that was the difference between fine-grained CFI on the left side and coarse-grained CFI on the right side. Because coarse-grained CFI is more efficient, but leads to control flow imprecision, as you can see here. You cannot, in a unique way, say this is 1 to 2, because you're using the labels, and there are many paths from 1 to 2. Yeah? And the adversary can find one of them, which was the case. Now, there were a number of, in 2013, 14, and also 15, there were a number of papers on this, and these are some of the most cited and most known ones, like K-Bouncer. And they also won the Microsoft Blue Hat Prize, which is $250,000. So for a PhD student, is not too bad. And they also used for example, EMET, enhanced at that time, enhanced mitigation experience toolkit. That is a protection mechanism of Microsoft, for example, in Windows, it is used. Okay, so then we are done, of course. However, that was not the case, because then in UseDix 2014, UseDix is a security conference, it's a very well known security conference. There was a whole track devoted to how to bypass these systems. And we had a paper there, some other colleagues had papers there, and they were all, so to say, targeting the same goals with a bit different approaches. But and I was wondering why the whole track is devoted to attacks, because there was a very, very important topic. And how it happened is that, just very high level, all these schemes have a policy, a CFI policy. You need this policy because the original CFI says every node in your graph gets a label. The coarse-grained CFI says not every one gets a label, or labels are repeated, or other policies that they use to reduce the number of labels. So there are all lots of tricks in these papers. If you're interested, you can look at them. But then what we did, for example, we start to understand what is the CFI policy. We start to understand how you can bypass it by listing the possible instruction sequences that are assembler instructions. This is a bit more low-level work. And then made a sequence filter to generate the gadgets that we need to bypass these policies. And these are examples like all kind of, kind of functions that we need to bypass every policy. The interesting thing was how to have a kind of more automatic way. So this is an effort which is at the beginning a lot of manual work, and at the end, most of it became automatic. So you get the policy and you create those instructions that you need, depending on the, of course, underlying computer architecture, that you need to build your attack gadgets. So they were all bypassed. So you see that lots of research went to a certain trend, lots of insight, of course. You cannot say, okay, it was nonsense. No, it was not nonsense. We got a lot of things because other people tried to break it. And the reason for that is that in a complex system, you don't have any means to prove security, mathematical proof. Of course, you can put a lot of effort in proving a piece of software secure with formal verification, which is, as I said, has its own limitations. But if it gets very complicated, it's very hard. Now, in that time, I had a call from Intel because we were working with Intel in certain part, and they were very interested to implement fine-grained CFI, not a coarse-grained, but in a smaller system like embedded system for automotive, for example, where you don't have a browser on an embedded system, you know, not a really too complex systems, and they had a platform which was called SysQ Peak. This is the name of the platform. It's an embedded system to have really CFI implemented in hardware. So with a lot of hardware support. And so we defined dedicated CFI instructions, and the paper was also the part that we could openly talk about, was published at DAC and received also Best Paper Award, which is among 800 papers is not too bad for students. But what was more challenging in this thing, besides implementing the CFI in hardware and taking care of the return instructions. Return is very important. As I said, you need to have a so-called shadow stack, so that at runtime, each time you have a copy of your return addresses, so that the control in the program execution knows to which return address you are going, and always check it to the shadow stack. And implementing shadow stack in software is very hard because the adversary may find it, and there are examples of that. So this is why it is in hardware. It is more difficult to attack hardware from the software than software from software. So that was but the most interesting part was that we had to design this in Darmstadt, and then send it to Intel, because Intel would not disclose to us their own microcode. So, and they had to check it and give us feedback without revealing any information about their code. And that was actually the most interesting, exciting part about it. So there are other examples of using hardware. So as you see, I am going towards the second episode where the hardware is now coming into play. In real systems like Intel CET, control flow enforcement, this is a functionality in hardware that we can use in the commercial products, and also ARM's BTI, branch target identification. These are hardware support for preventing code reuse attacks by means of control flow violation. So what are the lessons learned? I think, okay, I have enough time. The lessons learned about very short, very rough. Software defenses, they are insufficient for complex systems. So if you have malicious OS, all this control flow integrity in software do not work. And if you want to do control flow integrity for Linux or for Windows, of course, there are control flow integrity for Windows 10. Microsoft had integrated that, but it is coarse-grained. It can be attacked. So it helps in certain for example, it reduces the possibility of attackers to access all kinds of system calls, which are very important to attack a system. But it, in certain cases, if there are certain vulnerabilities, it can be bypassed because it's not fine-grained. It would be extremely inefficient to have a fine-grained. So hardware support is then helpful. People come towards hardware and say, okay, let's use hardware support to kind of get rid of the nasty code like operating system. Trade-off of software security and hardware support will be then the next problem. What is the trade-off there? And another aspect here is that, okay, let us then have some support in hardware and also run our sensitive code in a protected environment that is protected by hardware. Yeah, so specifically devoted to this. So this address range of memory is only devoted to a certain application, security critical application, and even the operating system cannot look into it. Yeah. Okay. So, is there any question before I go to the
Yes, sir. Good morning, sir. Hello.
No question?
Hello.
Yes.
Sir, I'm asking regarding the adversary point of view. So in the CFI attacks, we consider as an adversary as has the access to the whole memory. So after implementing any CFI check, when we go for testing, so what are the options? Because I have gone through some papers, so they are using like they will manually go to that particular register or that particular memory area and change the address. What I'm asking, like, what are the other options through which we can check this CFI? Like, how we can mount this attack on the embedded device point of view? I'm asking.
On the
Uh,
embedded device.
Yes, sir.
So if you have implemented, so to say, a fine-grained CFI on an embedded device, theoretically, you should not be able to simply bypass it, because in an embedded device, as I said, depending on, it of course depends on how you implement your CFI, of course, yeah. So if your CFI has hardware support, like specific instruction for CFI, yeah, so that you know, you use you just extend your instruction set with instructions that when it is when this instruction appears before, for example, a branching, because the branching is the part that makes security difficult, because the adversary also can misuse branching. And by the way, the adversary does not usually have is not really changing the memory addresses. The adversary is just misusing the memory address. The adversary needs to access certain memory addresses to get to the instructions that it needs. So if you implement it in a fine-grained manner, then principally for control flow, there are also attacks that are called non-control flow attacks or data-oriented attacks. You cannot prevent all of those with control flow integrity. You can only prevent control flow integrity attacks, which are, so to say, the most investigated, so to say, attacks. But in general, for embedded system, fine-grained CFI, theoretically, you should not be able to bypass it unless you have an error or bug in your implementation of the CFI. That is, of course, another issue that goes to the hardware vulnerability, but you should not be able to do that. If you do it coarse-grained, for example, you leave certain return addresses out. You just say, when there is a branching and the control of the program comes back, then it can go. It has the possibility, the options to go to several different returns. Then, of course, the adversary can misuse this. I don't know if I answered your question, but usually you should not be able to bypass a fine-grained control flow with a control flow attack. Yeah.
Thank you, sir. And one more question I have regarding the trusted computing base you told. So on embedded system, ARM-based processors, we have something called trust zone. So
Yes.
what are the options of clubbing this CFI along with the trust zone? Will it provide more security, or how these two can be related?
Yes, I will come to that. I think, yeah, okay. If we take another 10 minutes that we lost at the beginning, I will come to that. Okay, so let's go to trusted computing. What is trusted computing? Is actually, as I mentioned, you add some trusted component into your system, and then you expect the system to behave here as you want, yeah, or let's say as expected. Yeah. So just to give you an example of trusted computing landscape, since 90s and before, these are, you see a lot of names on the screen. These are very, so to say, the most known names, and I always extend them. They are not, of course, complete because they don't fit on a slide, but these are very old system, very new system, and I'm going to categorize it in the next 2 minutes. Yeah. So there are solutions that are from industry and academia, and these solutions they belong to the trusted computing landscape because they make assumptions about trust in certain components in the system. For example, those of you who have heard about trusted platform module, which is now meanwhile a grandpa of in trusted computing history. This is a cryptographic coprocessor that is actually typically in every laptop or server except Mac, for example, or some other system, but most systems have it. And it provides, currently it is used for example, it includes keys, cryptographic keys that are used to, for example, encrypt the system partition. Yeah. But some of you also have heard about Intel SGX, ARM TrustZone was mentioned before. AMD has its own development here. And on the other side, you see some things. I'm going to make it a bit more fine-grained. Here you see the part which is on embedded systems like ARM TrustZone. Almost all mobile phones have ARM TrustZone. And TrustZone is the security part of it. We'll come to that. Then you see here Sanctuary. It is from my group, which is a kind of progression, I would say, of ARM TrustZone, because ARM TrustZone has a lot of problems, also usability problems. Then TrustLight is on embedded systems. This is a project with Intel, providing a trusted computing embedded system. Hector 5 is a very new development in the RISC-V. I will come to that. And Java Card Platform, you know from those who know it, it's very, very old way of using hardware to support security in a system. Now, there are the so-called Enclave architectures that I come to. That means security execution environment for your security critical software, sorry. And here you see some systems, for example, Bastion is from Princeton, tries to have lots of memory safety aspects in hardware. Some of these systems are the so-called capability-based system, for example, Cherry from Cambridge, which is not really an enclave computing system, but it has, so for example, if you want to access a certain resource in your hardware, then there are capabilities defined for those accessing. What can access what? So this is more or less, you can consider it as a policy which is embedded into the hardware. So access policy. And some of these systems are deployed, as I mentioned, ARM TrustZone, which is also we can consider as hardware-assisted secure boot. ARM TrustZone has that as well, so to say, but other systems as well. There are some systems that are in a very, very recently developed on RISC-V, like Keystone from Berkeley, Sanctum from MIT, Cure from my group, Timber 5 from University Grass and my group. and Cfi, which is a RISC-V company that very recently provided a architecture of WorldGuard. If I have time, I will come to that. So, and some of these systems try to prevent or the so-called software, I call them software side channel attacks, which is, for example, like cache-based attacks. So now, what is an enclave architecture? Here you have your legacy system with not sensitive applications and system software. As I said, you don't trust operating system or system software. Enclaves are, you can say, containers that contain sensitive applications. And there is, of course, a trusted software that we need in software to use the SOC with hardware-assisted security mechanisms, because you need to devote memory to it, to these enclaves. The management still is done by system software, but you need still need a software interface to hardware, which must be trusted, because you don't trust for everything the system software. Now, this part, yeah, the features in the hardware and the trusted software are a part of your trusted computing base. You must trust this part not to fail. Yeah. If this fails, everything fails. Yeah. So, what is the adversary model in enclave computing? Again, we said we start with system software. This is operating system. We don't want to trust it. Also, any other non-sensitive application is potentially an attacker. So what are a bit more detailed, what are the attacks that system software still can do on our system, are the so-called controlled side channel attacks. What is that? For example, memory pages contain information that system software can get from the memory pages, because the management of memory is still by system software. Indeed, the management means, for example, the system software knows how much memory goes to this, how much memory goes to that, but it cannot really influence what is inside this memory, in this memory region. However, when there are translations of addresses, virtual addresses to physical addresses, the system software may get information, because here there may be a leak from the memory. This is called controlled side channel attacks. Now there is also attacks that can be done directly to the trusted software if there is a vulnerability here. As I said before, we need to trust this, but if we have means to verify this, and this is always the assumption, to have a software, let's say formal verification, because it's a small piece of software, then we have assurance that here there are not bugs, but we need to think about it. Then there is also no guarantee that in the enclave, because an enclave can contain anything, even the sensitive app itself can be malicious, or it can be even triggered from outside to become malicious by means of runtime attacks, if the adversary can find out through some leakage how this control flow works. Yeah. Or the malicious code is loaded to the enclave, because enclave does not guarantee that the code which is inside is not malicious. And then this can start an attack if there are some vulnerabilities known in enclave in general or in trusted software. So just attack surface I want to show you. And there are attacks on microarchitectural attacks, as you all know, like Meltdown and Spectre and alike. And this is happens when the microarchitecture is about execution of code and using registers and using buffers. And when at that level the processor is working, it leaves traces of information in memories for the reason of efficiency or design failure. Many processors, they leave this information there as it is. And if there is a way for an adversary, for an unprivileged software, for example, an application here, to see this information, yeah, that this information is made visible to a higher level unprivileged software, then we have all these so-called microarchitectural attacks. Now, I would like to show you a case study. I use SGX as a case study. That is Intel's software guard extension. This is an extension of a commercial CPU of Intel with security functionality, and very interesting. 15 years of development in general, and also lots of effort, engineering effort and money. And the leakage aspect, information leakage in SGX was completely underestimated. We will come to that very soon. So here is some prominent cache attacks on SGX, but before that, let us look at a very rough, or sort of very high-level architecture. Here we have, in the memory side, in RAM, we have the so-called enclave page cache. This is the memory which is devoted to enclaves. And enclaves are, for us, kind of the holy container. They contain my sensitive apps. Now, other apps are not trusted. As you can see, they are orange. OS is not trusted. At the CPU level, we have different CPU cores. At each core has two threads, which is called simultaneous multi-threading. This is a good thing. You can run two threads on your CPU, but in some cases, it's also a problem. Then very roughly, we have different cache and branch prediction, whatever the CPU uses. This is a very high-level view of that. Yeah. Now, there have been a lot of attacks that misuse, so to say, the caches and the internal buffers of the CPU, or internal caches of the CPU, to attack an enclave. Yeah? So an adversary here and tries to attack an enclave. Imagine, so you just don't forget that operating system is malicious. Yeah. So it's not trusted. That means the adversary has control over operating system and all other non-sensitive apps. Okay. Now, there have been a lot of attacks. Some most cited one I want to show you here. So let me go here. So some of the attacks, they try to use the information of, to extract information of, so to say, branch prediction. That is, for example, you can read this information, to use internal caches to infer the control flow of the program inside the enclave. And then they could recover RSA key, which was inside the enclave, because you need a key to encrypt and decrypt when you are communicating between two enclaves or enclaves with a normal system. Yeah. So these are two examples of how to infer the control flow. Other examples use attacks, standard attacks like prime and probe. This is a very known attack on cache timing. So you can see the timing between the changes between cache states. So reading from cache, so eviction and writing. And this time, depending on if it is the adversary can recognize if this time difference is from the enclave or from itself. This is called prime and probe. There are also other techniques by prime and probe. Because cache is a shared environment, they can get this timing information, and there are lots of problems to get rid of noise, but at the end they can detect AES key dependent memory accesses. But all these attacks, these two attacks, need to interrupt the enclave. But there is also a mechanism that you can use that the system understands, recognizes, there is the enclave is getting interrupted more than in normal case. So the system provides an exception. So these attacks would be then limited. Yeah. And we had an attack in 2017 where we try to, first of all, reduce so first of all, not need to interrupt the enclave, or at least that it is not recognizable. And also what was interesting is that most of these attacks, they try to extract a cryptographic key by observing the cache state. But we wanted to know if we can run a more complex algorithm in the enclave, because, you know, RSA and AES, becomes a bit boring. So we started to look into the more complex. At that time, an algorithm which was very interesting for us was a genomic sequencing algorithm, because we wanted to know if that was used by FBI to do a DNA matching. So we run this algorithm in the enclave, and by observing the cache state, we wanted to see if we can recognize when there is a match found by the algorithm from outside. So we have a reference value, and we want to understand through the observation of cache if this algorithm found this specific DNA. And that was very interesting that it's possible. So it's really exciting. And there are also other interesting attacks, like how one enclave can attack the other enclave by using prime and probe. And all this is happening because cache is shared environment. So this is not a big surprise, but what was happening is that cache attacks, side channel attacks, were not in the scope of SGX, at least at the beginning, as some people like me and others pointed that out. Of course, on the webpage of Intel, they put in a statement that this is not in the scope of SGX, because we know that we are using the shared environment. But what happened that the trust in SGX went down a bit, because the extent to which these attacks, which were mostly by academia, the extent to which that would harm their reputation was not clear at the 10 years ago or 15 years ago as they started with that. So this is what I'm saying. It's very important to think about the future when you design a system based on the legacy systems, because that was an Intel processor that they needed to extend in a lot of functionalities for security. And you have still legacy system. So now I had your cache side channel attacks, which was actually a problem for SGX. And now I come to those attacks that you have heard, and I'm not going to go into details because there's no time for that. But for example, Spectre attack, where you see in this picture that I put a lot of effort into make it. Here, the Spectre is like a runtime attack, as I mentioned to you, like return-oriented programming attack. It uses the gadgets that is found in the victim. So it's in the victim context. So one app is attacking another app by having certain vulnerabilities in the hardware. That is, the microarchitectural state is visible to this application. Yeah. Another one is meltdown. Here, one application is accessing one unprivileged application is reading from a privileged memory, for example, from kernel. That is breaking the OS privilege boundaries. And another one is foreshadow, where a system which has an enclave, so a system, these are not extended, this is a system which is not extended, the CPU is not extended with the security functionality like SGX, this is like a SGX. And then foreshadow is the name of an attack that breaks the actually boundary, in the sense that it can access the key, a very important key in an enclave. So that is not good for security. Actually, it is a disaster. So, and what is this disaster? So in SGX, you have an enclave, which is called the attestation enclave or quoting enclave. This quoting enclave, is so high level, very from abstract point of view, it vouches for other enclaves. So if because if I want to communicate with a code inside an enclave, I want to know if the code is really running in a real, genuine enclave. And this trusted enclave is kind of vouching for them. It provides certificates for them. And for that, it has a signing key. This key is a very holy key. So people started to use Meltdown to access this holy key. And once you access this holy key, then you cannot trust any enclave to be genuine because the key is revealed. This is signing key. Yeah. But of course, the first attack was these attacks were from L1 cache because they could load with the tricks of Meltdown. They could load the cache into the key into the L1 cache, and of course the adversary could access it. But that was a relatively easy fix by Intel. They could fix it, but still they had to fix it by flushing the L1 cache. So they could do it at microcode level. But then there were other attacks that used, for example, return stack buffer in the CPU by mistraining it, that it used then spectre. That means if the return address are mistrained, then it jumps to the code control jumps to a gadget inside an enclave. This is a bit more complicated, but in general, Spectre, Meltdown, and the combination of them are used to access this key. That is another problem that SGX had to, so to say, live with. So the question was, now this is the question that I always put in my talk, was SGX a failure? My answer to it, and everybody can think about it who has worked with SGX, I think it was not a failure. It was the designers didn't expect what the future development will be. At least this is what I speculate, although I'm in business with Intel for many, many years, but I think that it gave us a lot of insight, and many, many PhD students could make their PhD with the SGX, either attacking it or trying to protect it or whatever. So now we come to the question, and one of you asked the question about ARM Trust Zone. Now, is ARM Trust Zone a good thing? What is ARM Trust Zone? And I go immediately to limitation. ARM Trust Zone, which is also very, very old technology, divides the world into normal world and a secure world. In the normal world, you run your legacy system. In the secure world, you have your so-called trusted apps, which is running on a trusted operating system. This is CPU mode that when an application wants to run here in this normal world, a security critical operation, then the secure world is booted, so to say, just abstractly. And here then you run the operation, and then you give the output then again back to the normal world. And these are the trusted app, for example, a payment app. Yeah. Now, these trusted apps are separated inside the secure world by isolation of a operating system. So they have a software isolation. Trusted OS provides process and memory management. And we have also a trusted firmware here, because you still need to access the extended system on chip because of this secure world CPU mode. And also in the memory, so your resources are also divided into secure world and normal world. So, and here you have a rich interface. Why is a rich interface? Because if any of these apps becomes malicious inside the secure world, because it knows vulnerability in trusted hardware and implementation vulnerability in trusted operating system, then it can, of course, misuse it. Note that these apps have access to privileged operations of trusted operating system, because they are all running in the secure world, and they all belong to the so-called trusted computing base. And as you can see, this secure world or trusted computing base is also only a one single enclave. Yeah. So trust zone mainly locked for device vendor services. So that means, for example, Google and Apple would not put their payment apps in one enclave because they may not trust each other. This is why developers never really use trust zone. Only device vendors use it for their own system software. Yeah. So or keys or whatever. And then you were asking that trust zone can help. Yes. In CFI, for example, trust zone can help to protect the labels because the adversary should not be able to overwrite the labels. Then it can run the attack. So, and many other things, trust zone can be of help. However, as you see, there is only one enclave here, and developer cannot use it. So in SGX, you can have an app which is running an enclave, another app which is running an enclave. So you have theoretically arbitrary number of enclaves. Here you have only one enclave. Yeah. Now, enclave computing research. What do researchers do in this area? So some are looking into this controlled side channel attack, so attacking the system. This is more offensive research. The memory pages, don't forget that your system software can try to leak information from memory pages. The microarchitecture attack is still a case. People don't get tired of it. Implementation flow exploitation is one thing. So what are the implementation problems here? But it is more implementation, nothing conceptual. Enclave architecture design, this is on the defensive research. That is, for example, my group is doing both anyway. Side channel resilient caches, designing caches of such an enclave hardening. So inside the enclave, for example, putting CFI inside the enclave, that these applications cannot be attacked by control flow attacks. Yeah, so enclave hardening. Then enclave use cases, and in some cases, in some research, people say, I don't care about all these problems of enclave. I assume that the enclave is secure, and then I run machine learning stuff on top of it. Yeah, try to protect my machine learning algorithms. This is also a line of research. Now, I told you that trust zone. Now we come to enclave design enclave. Trust zone has only one enclave. So our question was in 2019. Can we use trust zone in such a way that we can have more enclaves? To a simple question. And this means that if we have systems have usually more cores, and the question was, can we take one core and we use the same security primitives as the vendor? So in the software, we have the vendor, and then we start to replace, so to say, at the runtime, we choose one core, for example, for a security critical application, a sensitive app. And in that way, in core A, this is a normal trust zone. In core B, for example, a sensitive app is running. It is isolated from other cores, or we can run it in a core C. So we have two sensitive apps running on two enclaves. And this allows actually the developers to provide, so to say, to develop apps that are sensitive and do not need to run in the trust zone where only vendors' security primitives are running because vendors want to protect them. But then we can give the same guarantees in the user space by separating a physical core, so it's a physical separation, and when they have a so to say shared cache among the cores, for the time that this is running, we just don't let others use that shared cache. This is a performance limitation, but in a modern fast system, we can do that. So that indeed led us to a new way of using trust zone, and without changing the hardware. But why? Because, let me give you a bit more detail. This is called Sanctuary. It was presented at NDSS 2019. This is the view of the system. You have your memory controller, bus, system, shared cache. You have the core, which is a typical trust zone, and you have another core when sensitive app is running here in an enclave, which is you can consider as a core. It is still trust zone core, but now it is sensitive app. And how do you identify it? We actually misused a function that was implemented on the bus of trust zone to. This is one of the implementation of trust zone. It is trust zone is only a kind of on paper, but how you design it is a different thing. They use that, so to say, addressing a peripheral. So, for example, a GPU. We misused it to address at runtime a core for when a sensitive app wants to run. Yeah. So just to show you, you can still use legacy systems if the implementation allows you, if those who implemented thought about addressing a certain peripheral, for example, and we can misuse it. And indeed, I called ARM and told them, are you aware of such a functionality? And they said, no, because the implementation that we use was by a big Chinese company. And we found that there is a addressing system that we can use it. Yeah. So because we knew what we wanted and we found it in the implementation of them by hacking actually in their system, in their implementation, looking at the implementation. So that was very interesting without changing the hardware. So, okay, I don't come to the evaluation. You don't need that. What I want to go in the last part of the talk, which is in some minutes, will be finished, is I think I need another 10 minutes and then I'm finished, is a next generation industry solution for enclave architectures. So one of them is the so-called secure encrypted virtualization that is from AMD. Again, you see the typical architecture. You don't need to understand everything. You just need to understand the concept. Here, you have, again, your legacy system, and then you have the so-called runtime enclaves that are virtual machine enclaves. So how do we separate these enclaves from each other, that they have hardware support with the help of this secure processor here? This secure processor allows each of these enclaves to be encrypted by means of, it encrypts them. It is configured to encrypt any enclave which is running the whole operating system and an application which is sensitive. And this partition, which is a virtual M, you see, you still have a hypervisor. You don't trust this hypervisor. And this, for example, an operating system or hypervisor can try to read this VM, but it doesn't have the key because the key is in the hardware. Yeah. So reading from each enclave is encrypted with its own key, and this is also reflected in the memory. Yeah. So this is how the access control is done, or separation of enclaves. So this part is a new part, but as AMD came up with this, there were a number of attacks. First, the attacks, they were more cryptographic nature because they used encryption and not authenticated encryption or integrity checked encryption. Then there were attacks by hypervisor because they were still controlled side channel attacks. The hypervisor could read could leak information from memory pages. In Intel started, after learning a lot from SGX, they started something which is called trusted domain extension. And here, you try to run the same virtual machine. Don't forget that SGX is running only an app in Enclave. Here, you run the whole operating system. This is your goal, because for practical aspects, you need to, actually, you're going to the back, very old systems where you have a hypervisor and virtualization. Now you want to have your enclave even protected against hypervisor, because in the older systems, the hypervisor is always trusted. Here, not. Okay, so Intel TDX, Intel Trusted Domain Extension, has learned from the mistakes of secure encrypted virtualization by AMD. They have also a memory encryption engine, but they have also a module which is called TDX module. And this TDX module is, through a CPU mode, is also kind of isolated in hardware, but with hardware support. For example, is sensitive VM structures like page tables. Yeah, memory, this is the memory pages and page tables are stored in memory of TDX module and are not accessible by hypervisor. So this information about the translation of memory is not available to hypervisor. And here also encryption and integrity protection, or integrity protection is added to the encryption, so there are some attacks prevented. So TDX, as I mentioned, learned from initial SEV mistakes. Of course, SEV is trying to fix that, and they have newer versions. So here TDX is not, as far as I know, not really a product. Intel intern, they have access to it, but sooner or later everybody will have access to it. As you can see here, none of these systems can have a solution against cache. The cache is cache side channel attacks. The cache is still shared, so you have still a lot of possibility to attack the system. What here is protected is more, so to say, the obvious things that, like sensitive VM structure, because they wanted to prevent the obvious things, but shared cache still for efficiency they need it. Now, let me see. There is also the same very similar one by ARM. ARM now, this is actually the idea that the architecture of a new ARM, which is for 4 years now there, but it's not implemented at all. This is an idea. This is also what we were always telling to ARM. I don't go to the detail, but you can see that here they call it Realm Enclave. They're all the same, but now, as you see, they have in their normal world, they call it Realm world. You can, the developer can run an enclave in the whole, so to say, runtime enclave with operating system inside the enclave. Actually, from conceptual point of view, is what we did with Sanctuary, but it is certainly on the, you don't need extra core for that. Yeah? We use extra core because we wanted to use the legacy system. So, and I really, this is just for you to know that all these companies are thinking about the same, not the same, but similar security architecture. And these are the new, so to say, concepts, new components in the hardware, like memory protection engine, as you can see with Intel and AMD, and also things like memory management unit and something that they call granular protection check. This is a kind of policy check, what component is going to access what. Yeah. So they have a third level of address translation. This is the GPC, making use of a table, which is called GPT, just to have a more fine-grained access control. Yeah. And the MPE is just to, so to say, protect against physical attacks, because everything is encrypted. So physical attacks cannot access the memory, but I mean, they can access the memory, but they cannot, they can just read encrypted stuff. But as I said, hardware attacks is not our focus here. So let me go to the last part, which is on RISC-V based enclave architectures. So, and the reason for that is, this is the last episode, is open hardware design. Open hardware design could be the right decision in the right direction, because all these processors that have design problems or optimization aspects that lead to security vulnerabilities, they can be kind of fixed, maybe, in the sense that when we have at least when we know what is in our hardware, yeah. But it doesn't mean that we will have perfect security, no, because open hardware can have also lots of problems. So here I just show you very short difference. I mentioned Sanctum from MIT. Sanctum tries to actually get rid of problems of SGX. This was as SGX came out, they looked into it. As you can see, they provide Enclave at the user level. They have something which is called Security Monitor. This is the software that you need to trust. And they use MMU for access control. Because it was very first architecture on RISC-V, security architecture on RISC-V that tried to, for example, provide also cache partitioning. Yeah. The second one, as RISC-V emerged, they started to standardize RISC-V and adding more components. I will come to that. So Keystones from Berkeley, and again, they have provided the so-called runtime enclaves. Yeah. So like the virtual machines that I showed you, but it is not running on a hypervisor. It is another design. They don't need it because RISC-V has, as I said, it has open source aspect. You can change a lot of things. But in the standard, they provided a component. It's called PMP, and PMP is more for physical memory protection. That means it does actually what this changed MMU did for Sanctum. It provides, it is configured to protect the enclave memory, and certainly Keystone also added cache partition in the sense that side channel attacks would not be possible, or the effect of them would be tremendously reduced. We started to ask ourselves, hey, they have Sanctum has user space enclave, Keystone runtime. Why? But in a number of applications, we need different kind of enclaves. So we started to look into different kind of enclaves, user base, a system that provides runtime enclaves as well. So you can run the whole application. You can run your drivers, for example, in enclave, but also the security monitor within the whole firmware. You don't need to trust all the firmware. Maybe you have a security monitor also in an enclave. Actually, Keystone has also for security monitor an enclave to protect it, but we think that we have a much smaller security monitor. And beside that, we also would like to have something that actually Trust Zone had, and that is a secure channel between an enclave and a peripheral. For example, if you have an AI chip, you run your machine learning algorithm here, and you want to have this AI chip connected to the application that is running. This is the software application that is running in an enclave, and you don't want any other component in the system to have access to it. So it's a secure channel, and this is done by a filter engine on the system bus. Okay, I think that's enough for this. I don't go through the details of Cure. If you are interested, you can ask me questions. The lessons learned of all hardware-based security is that cache side channels seems not to be a concern of industry. So all the development that I showed you, SGX, TDX, and others, they don't have any cache side channel protection, which I think it is, again, a mistake. Enclave architectures seem to become highly complex because they want, you saw the design of ARM. I don't think that anybody is going to implement that because it is too complex, because they want to have backward compatibility, or always having legacy system with you. Multi-enclave architectures, as for example, Q, as we did, they provide more flexibility, I think. but we will see in which area they are going to be deployed. But all the RISC-V security architectures provide cache partitioning, which is a plus, I think. And the idea not to trust operating system and hypervisor sometimes contradicts the original idea of enclave architectures, because still, as I mentioned to many of these systems, they have this problem with control side channel attacks, the page table translations. This is the memory that is the information that is leaked to hypervisor or to OS. So here we need to have some good solutions, and there are some ideas how to do it, as I showed you in the case of TDX. Okay, and to end it, for those of you who are interested in learning more, there is the aspect, as I mentioned from the beginning, the software exploitable hardware vulnerabilities are the most important security aspect, at least for me. And in the last 3 minutes, just to show you that we are not going to get rid of hardware vulnerabilities, and you see here there are some of the known attacks. Some of them are cache attacks, some of them are hardware vulnerability, the real hardware vulnerability. I mean, when I say real hardware vulnerability, that means hardware vulnerabilities that go beyond microarchitectural vulnerabilities. These are vulnerabilities that many people don't know of. And you see that all these attacks have cool names, but sometimes the names are much more creative than the content of these papers, because they're all very much the same. But somebody accepted these papers at the conference, including our papers. I'm not just saying that we are an exception, but what happens that, as I mentioned several times, hardware cannot be patched in silicon. So what can we do against this? One way is to find hardware vulnerabilities. And we started 2018 with Intel, and later on with Synapses and Texas A&M, to run one of the largest joint industry academia hardware security competition. It is complex. It is going over several months. We implant real-world hardware vulnerabilities, and thanks to Intel, we got a lot of insight about vulnerabilities that nobody knew of, because they were found short before the production of the chip. And if they found afterwards, that's a disaster. And we tried to extend them. We tried to make them or understand them in a different way by looking at it from a different angle. And several CPU designers at Intel help us to have more insight. And we've implanted this in RISC-V processors that are getting more sophisticated, and currently provided in this competition to teams. And these bugs are at, for example, RTL. If you don't know what RTL is, that doesn't matter. It's you can assume it as a kind of hardware code, yeah. And it has, the bugs are, so to say, in system bus, in peripheral, in cryptographic engines, processor core, you need JTAG interfaces, boot ROM, which is the target of many attacks. And you're looking from different aspects, different angles, denial of service, how you can really completely destroy the chip or a functionality, how you can do privilege escalation, yeah. And all from software point of view, it is software exploitable. Sensitive information leakage, for example, microarchitecture attack and other leakages, or how you can, as I mentioned, how you can exploit these vulnerabilities by software. So the teams don't know about the exploits, about the vulnerabilities. This is, for example, from 2018, a list of bugs. If you are interested, you can go and read this paper at Usenix 2019, and you can see also the video of it about how we run this competition at different conferences, at that conference, which is an established system conference, at Usenix, at CHES each year, and they have different scope. And these are, for example, some examples. And interestingly, because we implant in this RISC-V, different groups must have arguments, have reasons how they found their bugs, with which tools or with which methods. Otherwise, they don't be considered. And you will see a variety of approaches, from formal methods that sometimes doesn't work and that cannot find a number of serious bugs, to human intuition, which is the most successful one. Until now, in the last 5 years, our observation is that human mind is the most effective one. Crazy approaches to come to the goal. So here I give you just one example. We put in this platform, you see all kind of components are have bugs. We have implanted bugs into them. Just as a example, for example, this AXI bus, it is a bus protocol that allows you to connect to other components from your CPU, or components can talk to each other. Now, the bus state machine has a bug. I call it bug, but it's a security and design vulnerability. What does it mean? If it depends how you access the memory, want to access the other component or memory with this over this bus protocol, the state machine ignores memory access faults that occur in a particular sequence. That means if you access the memory and you get it is over this bus and you are doing unprivileged access, the bus controller tells you no. But if you get this exception, no, and directly afterwards you send another illegitimate access to the bus, it slips through. So it is a problem of the, so to say, as a faulty transaction. If you do it in another order, everything is okay. But in this order, then the state machine cannot handle it. And finding this attack by a formal method is not very easy. And some people could find it just by intuition, and of course some way of analysis. So I don't go to other, there was also a bug that people found that we didn't put in the RISC-V, but that was a RISC-V implementation bug. That was also interesting insight. For example, faulty logic in the real-time clock. If real-time clock is faulty, then all the digital rights management and certificates are also faulty. Okay. What do we do as research? Very short. What we want currently to do, and that's my last slide, is something that you can consider as a vision. Let's say you have a processor with fixed logic and reconfigurable logic, but reconfigurable logic are all those components in the chip that are security critical. And when I say reconfigurable logic, you can think about something like FPGA, but I mean something different, a bit tweaked technology that is upcoming at the low level, so that you can have some assurance against unknown attacks. So we can't really always fix some attack and say, okay, we fix microarchitectural attacks. Even if you fix them, then there will be another attack. So how about making hardware chips as flexible, or at least to some extent flexible, as software? There are, of course, microcode patches. There are approaches where certain components are reconfigurable in hardware. But I'm talking about all the security critical components, and that provides a number of questions. The first, so here you see some components that are security criticals, and we want to have the fixed logic for performance, and we want to have reconfigurable logic for those critical aspects, only for those critical aspects. Now, the question is how to identify and map these security relevant elements to configurable elements and units, and how this configurability technology should look like. How do we have a optimization strategies for security performance, power, and area trade-off of configurable units? This is what is well known in hardware community. But how do we do that when we not want only one component? We want all distributed all over the chip, all kind of security relevant things, if we even can identify them. Or let's say we go for one, that is what we are following, with one part, that's information flow or leakage. Validation of configuration strategies is also very important. How do we do it? With what methods? Formal methods. And here we chose fuzzing because fuzzing is in software community a big thing in currently in security community. We have thousands of fuzzing papers like CFI, and this is why I showed you CFI and runtime attacks, because that was hot at that time. Fuzzing is now hot today, but we don't know what is coming later. And fuzzing is just random testing, but in software it becomes a bit more sophisticated. In hardware, there have been research in the last years, or let's say reinventing hardware fuzzing, making it more accurate or more effective for hardware. And then here, both in case of configurability and hardware fuzzing, we have some, the first steps we have made last year and this year for example, having a configurable cache architecture. So your cache partitioning is done at runtime. The cache controller is with runtime, and I'm finished now with the last line. And we have we had that Usenix this year, some 2 months or 3 months ago, a hardware fuzzing paper that tries to really comply to what is known in hardware design community with regard to coverage when you want to verify hardware. And there is a work, it's upcoming, that is combining hardware fuzzing with formal methods. And with that, I am finished, and thank you for your patience. Any questions?
Sir, I have a question regarding tools. So, so for the CFI, you told regarding a basic block level testing. So if we take the example of the LLVM compiler, so there we write the LLVM transformation passes to update the code for these checks for CFI.
Yes, you can do that, yes. And that is what you should do actually.
And
when you have access to the source code, yeah.
Yes, but I want to know, are there any open source tools available so that we can go one level further, or we can add that to make it more efficient?
What tool make it more efficient?
See, going through this compiler technique, like writing this checks at the basic block level, this is one technique. Are there any other things which are available as open source tools which I can utilize for CFI?
Okay. So tools for other tools for CFI. So rather than compiler?
Yes.
To be honest, I don't know. In 2000, so in 2016, I just continued in my group with research on CFI to just use it for what we call runtime attestation. So that you know at runtime what execution path a system is taking. But I am not aware of anything, but I've heard there are a number of publications. They are not commercial tools, they are research tools to approach CFI in a different way. But I am not familiar with those, with the details of those papers. I just heard from colleagues who are working on that. Yeah. Sorry,
Okay, sir.
I don't know any
Okay.
other tools. And yes, if you have compiler, that would be the best way to do it. Then if you want to have it fine-grained, you need to take care of shadow stack. And for example, Google does something which is called forward CFI. They use their design tools to take care of all the forward branching, not the backward branch. Backward branching, as I said, for returns, which is very important, you need shadow stack if you want to do it right. And Google guys say, okay, for returns, we have other methods like canaries. They are not so effective like backwards CFI with shadow stack. But it's a compromise for efficiency and the fact that you don't want to use specific hardware that provides shadow stack for you, like CET from Intel. So if you don't want to use that hardware, say I want to run on every hardware and still have CFI to some degree, then they use actually their own compiler for that to insert the labels. But what other way of doing that, I don't know.
Okay. And if I have any specific question related to this, so can we mail you?
You can definitely send me a question, and if I cannot answer it myself, I can send it to my guys who are much more expert in certain areas than I am, and then we send you the bill. No problem.
Yeah. Thank you, sir.
Any other question? Okay, if not, thanks a lot, and thanks for the invitation. And I will then close this session, right? Or
hello, Professor Ahmed. Yeah, are there any more questions? Okay, so if no, then let us thank Professor Ahmed. If you want, you can go to the participants. If you want, you can go to the reactions and you can maybe put the clap emoji, something like Shell did. So.
Okay, so I don't
thank you so much, Professor Ahmed, for being with us in an early morning of the weekend. We really appreciate your time and effort, and thank you for enlightening us with your journey, your experience, and your vision on system security. I am sure all the participants have been greatly benefited. And if you have, like Professor Ahmed already told Praveen, if you have any questions, then I guess he will be happy to take that.
No, that's from my side. Thank you very much. And if somebody is interested in what I call security, the last slide, security adaptive hardware, and they want to do research in that area, they can contact me. I have some open positions currently. Looking for really good people who are really interested in hardware security, and we have a very exciting project there. Otherwise, thanks a lot again, and hopefully we see each other in person sooner or later.
Yeah, okay. So a lot of participants are also saying thank you for the excellent presentation. Thank you, sir, in the chat box.
Thank you. Yeah, I saw it. Okay. Have a nice day.
Okay. Bye.
Bye.